Physicists reveal that these strange black holes are devouring the Earth from within. Primordial black holes, or PBHs, are cosmic remnants that could have formed in the early universe, long before the appearance of stars and galaxies. Cosmic archaeology, you might call it. These small, dense entities could theoretically explain some of the most persistent mysteries of modern cosmology, such as the nature of dark matter. So far, however, direct detection of these objects has proved elusive. A recent study raises a fascinating prospect. Primordial black holes could be hidden inside planets, asteroids, and even in everyday objects here on Earth. This paper, published in Physics of the Dark Universe, explains how these hypothetical objects could capture or partially consume planetary bodies, leaving hollow structures or microscopic tunnels that would be detectable with current accessible techniques. Primordial black holes, origin and main characteristics. Primordial black holes are a hypothetical type of PBH that formed due to dense fluctuations in the early universe. Unlike conventional black holes, which arise from the collapse of massive stars, primordial black holes could have tiny masses, from a few tons to the equivalent of Earth mountains. This makes them very different in behavior and gravitational effects. These objects also formed because of the extreme density that the universe underwent at the beginning of its expansion. The study suggests that these objects may act as silent devourers, trapping materials around them or consuming liquid cores in planets and asteroids. If one of these black holes were found inside a planetary body, it could form a hollow structure if the outer material is strong enough. Evidence on Earth and in the solar system. On Earth, the search for microtunnels in ancient rocks, glass, or even buildings could provide indirect evidence for the presence of primordial black holes. The paper explains that if one were to pass through a solid object, it would leave a thin tunnel, proportional to its Schwarzschild radius, which would be visible under an optical microscope. This distinctive feature would distinguish it from micrometeorite impacts, which usually leave craters instead of tunnels. In the solar system, asteroids such as Bennu and Ryugu, which have unusually low densities, could also be candidates for containing the trail of primordial black holes. Although the most likely explanation for their low density is their rubble pile structure, these objects open up new opportunities to observe asteroids that could have been transformed by interaction with a primordial black hole. The rubble pile structure refers to asteroids that are not solid blocks, but conglomerates of rocks, dust, and debris loosely bound together by gravity. This type of structure explains why some asteroids have a lower density than expected, since they contain many empty spaces in their interior. How do hollow planets and asteroids form? The study posits three possible scenarios for the formation of hollow planets and asteroids due to interaction with a primordial black hole. First, the planet can form directly around a small primordial black hole or capture it at its center after its initial formation. This allows the primordial black hole to become locked into the core of the celestial object, beginning its influence. Second, once captured, the primordial black hole begins to slowly absorb the central core, which generally has a higher density than the outer shell. If this outer shell has a high enough compressive strength, it can remain structurally stable, creating a hollow object. Lastly, if the liquid core of the object solidifies before it is completely absorbed by the primordial black hole, an empty cavity will remain between the solid outer layer and the remains of the core. This theoretical process could explain unusual internal structures observed in some asteroids. These scenarios provide a conceptual framework for investigating peculiar features in planets and asteroids, such as their possible hollow composition. Limitations and future possibilities. Although the study's calculations are promising, the probability of finding primordial black holes using these methodologies is low. The authors estimate that even in billion-year-old rocks, the probability of detecting a tunnel would be extremely small. However, because of the low costs and effort required, they argue that this possibility is worth exploring. The article mentions that current technology is already sufficient to begin preliminary searches. A simple optical microscope may be sufficient to detect microscopic tunnels in ancient samples. This approach, although limited, could provide valuable clues for future research.